Can you hear me now? Yeah. Thank you, Ross, for the introduction. And also thanks, of course, for to the organizers for inviting me to give a presentation here. And I also want to thank Tom for setting the stage, for showing us about the beauty of amorphous materials, and also highlighting some of the work of my group, which we do in the glass field. So today I'm not going to talk about MOF glasses. I will talk about flexibility. This is the second thing which is interesting us a lot. And when you think about flexibility in MOFs or responsiveness, what directly comes into your mind will be something like this. I think Hori Moon said it on Monday in her plenary lecture. Probably the most beautiful thing in MOFs is their flexibility, right? And I think we all agree on that. And what you have in mind is this behavior that MIL53, for example, shows, so this wine rack-like flexing behavior, which is just beautiful, and you can get drastic changes in pore volume. For example, then use this to separate gas molecules, or you can also switch between two phases with pressure, mechanical pressure, or with temperature. And what we are interested in, or worked quite a lot on, is this material, which is also this wine rack structure, which is DMOF1. I think most of you know it. It's around for a very long time. It's a beautiful structure constructed from paddle wheel building units, linked by this terephthalate linkers to form this 2D network, square grid. And then, and then you have the DAPCOs to pillar these layers in the third dimension. And this framework is already quite flexible in this non-functionalized state. So when you absorb different gas molecules in it, you have different structures. Yeah, you can see a flexing of these layers, and the structure accommodates different gas molecules and fits its structure to the gas molecules. And what we were interested in to tune the flexibility of the structure by functionalization. And the simple approach of isoreticular chemistry, you implement linkers which have additional donor groups, dispersion energy donors we call them, or dipolar energy donors, so groups which are flexible and point into the pores of the framework. And these groups typically are disordered in the structures. And the framework itself is crystalline, of course. And then these groups change the potential energy landscape in a way that when you take out the gas molecules, the structure transforms into this narrow pore form. And when you reabsorb gas molecules, it goes back into the large pore form. So basically, these donor groups here interact with each other, yield the dispersion energy, which is needed to have a distortion here at this paddle wheel to contract the structure. And interesting is you can even do this with temperature. So you can switch from the narrow pore to the large pore phase also by heating. So then the transition is not governed by enthalpy, but by entropic effects. So you have a vibrational states of the functional side chains, which are then populated, and then you go to the large pore form. And this is, you can use it, so this is so far unpublished material with a new functional ligand that has not an oxygen bridge here, and that also has a phase transition from a narrow pore to a large pore phase. And you can do this phase transition also by adsorption of hydrocarbons. You see here that this transition from the narrow to the large pore phase is dependent on the hydrocarbon you use. And this is quite interesting because with propane, you have a lower transition pressure for the phase transition than with propylene. For most other flexible MOFs, it's the other way around. So this could be used to separate these gases properly. But what I want to talk about today is what can we do to get flexibility in materials which are not flexible by definition. So this goes back a long time. Christian Serre and Gerard Ferret in 2009 in this review article, they told us why this famous MOF structure, MOF-5, is not flexible. Now, the topology of MOF-5 in principle is flexible. Yeah, it's a PCU topology. There are many MOFs with PCU topology which are very flexible and responsive, but MOF-5 is not. And the reason is the building unit, the inorganic building unit, because you have the orientation of these linkers here is in a way that only half of the linkers connected to this building unit can do this hinging motion, and the other half cannot. The reason is they are oriented simply in the wrong way. And as a result, this structure is quite rigid. That's also one of the reasons why this structure was so successful initially, and you have this high surface area material. And we were asking us a question, what can we do when we have this structure and we implement, again, dispersion energy donors and try basically to pull on this structure from the inside. And yeah, this is how you do it. So you made a series of these functionalized terephthalate ligands decorated with these alkoxy chains, several chain length, and then do isoreticular synthesis again, get beautiful crystals, cubic crystals of MOF-5 type materials. And that works very well. Get the powder diffraction patterns here. You see a comparison between the diffraction patterns of the different materials with MOF-5, and you see they are cubic except for one, this one up here, that is quite different. It has a different color, but it also has a different pattern. So when you look into the details here, you see that there is peak splitting going on. And an expert in diffraction, in rhombohedral transitions, you will directly see that this is a rhombohedral distortion. So this is a MOF-5 derivative, which has distorted along one cube diagonal. So basically it has done this one here. Sorry. It has done this one here, which I told you MOF-5 doesn't like to do it due to the geometry of this building unit. So it seems to be a bit flexible. And when we look in the crystal structure, so we get beautiful crystals of this. So you get the crystal structure of this material decorated with these long CA chains. Interestingly, these chains are ordered in the material. So it's quite packed already. There's some void space left, but it's quite packed. So everything orders. The linkers order. And you see there's a slight deviation from the 90-degree angle. So it's no more cubic, it's a rhombohedral structure. So far, so good. You look into the details, you see what is the driving force of rhombohedral distortion. There are dispersion interactions here between these side chains and the backbone of the framework and other side chains. And this results in a slight distortion of the node. So we have to distort the node in order to have this rhombohedral distortion of the structure. It cannot do it like a paddle wheel where you just have this hinging. The node has to change a bit. And so you get basically these oxygen atom here in the center of the node is moving up a bit, and the zinc atoms here are coming out a bit. Therefore, this bond is a little bit longer, and this one is a little bit shorter compared to the conventional MOF-5. So it's a slight distortion of the node, which then results in the rhombohedral distortion of the entire structure. So you have slight changes in the angles. Okay, now these have been the synthesized materials. So gas molecules in the pores, which also solvate these side chains. When we now take the gas out, something weird happens. First of all, for the material with a C7 chain, you go from the cubic to also the rhombohedral state. So it contracts as well, a little bit more even than the C8, and you have a rhombohedral structure. For the smaller side chains, yeah, as a synthetic chemist, you would say, okay, the structure collapsed and we just throw it into the bin. What most people did in the past, I think. But when you look into the details, you see, okay, there's some broad peak here, some broad scattering peak, and this peak gets broader and broader. So is it just a collapse? Is this completely disassembled framework? Does it not survive the removal of the guest molecules? It does survive. When you take these non-crystalline compounds and place it in DMF, for example, you go back to the crystalline phase. So far, so good. Many people have reported that. It may just be that you get a recrystallization because DMF is a good solvent. It solvates the building units, and then everything is reconnected, and you get a reconstructive recrystallization. But that's not the case, because you can also do it with octane. So a molecule which is unable to dissolve any of the MOF building units. So when you put it in octane, heat it a bit so that the octane can go in, you go back to the cubic phases, except for the C8, which still, it seems to love the rhombohedral structure. So that's quite fascinating. So you can follow this with also on a single crystal level. So these are reconstructed reciprocal space maps. So a slice through the reciprocal space for the synthesized DMF containing material, for the dry material, really cracked crystals. Due to the strain, you see diffuse scattering, but this diffuse scattering there's texture in the diffuse scattering. So this is not amorphous in a sense like a glass. You still see the fourfold symmetry. So it's not, I would call it non-crystalline, but it's not a glass material. And it's also not amorphous. There's still retention of the topology, apparently. And then when you put it in octane, you see that the crystals get clear again, surprisingly. And you can analyze the crystal structure again and get nice reciprocal space maps again. Fully reversible process. That means there's not a breakdown of the structure. There's just a distortion, and a distortion that results in loss of long-range order. When we look into the details of the powder diffraction pattern, here's the first peak of the powder diffraction pattern of the dry materials compared to the position of this peak for the simple MOF-5. That is a dashed line. You see that this reflection or scattering peak is shifting to higher angles or higher Q. And that means, so the smaller the side chains are, the stronger the contraction of the material is. You can make a simple cubic approximation. So basically calculate or determine the position of these peaks and calculate the corresponding D-spacing. And then do some simple math. So approximate this non-crystalline structures as a cubic structure still, and then you can calculate the volume change. And we estimate volume changes of about -3% for the rhombohedral one, which is consistent with the crystallographic data. And this goes then up to 17% volume reduction for the C2 material with a very small side chains. And this is this contraction we calculate from the diffraction data is consistent with pore volumes measured with carbon dioxide adsorption, which tell us basically the same thing, that this material is contracted by about 17 to 18%. So, but what's going on now? So how does the structure look like? It's a complex structure. So this is a PDF of one of these materials. So the C3 is shown here. You see in the synthesized, so DMF containing, and in the octane containing case, you have nice correlations, sharp peaks going up to 40 angstroms or higher. So that is a crystalline material. The dry compound, which is non-crystalline, you only see correlations up to about 15 angstroms. And this is roughly the distance from one cluster to another cluster. So one zinc oxygen cluster to the next one in this material. So that means you have the short range order, similar to as you have it in MOF-5, but then when you go to the next cluster, there are distortions and they are displaced with respect to each other. What you also see is when you look into this distance B, that is the zinc-zinc distance in the cluster. This distance is very sharp in the crystalline case, so there's only one kind of zinc-zinc distance in the crystalline materials. In the non-crystalline material, it's a broad signature. So this is a representation of the distortion of this cluster. And it looks like it's not only one kind of distortion of these clusters, there are several different distortions in this material, so it's very highly disordered, and there's not only one configuration which describes the structure. There are several different ones. But then you can go back, putting octane in, and you're again crystalline and sharp. And now when we compare the entire series, so with the different carbon side chains, we see here, these are the rhombohedral ones, they are crystalline. The C6 is a bit of a border case. So there's some correlations here still, but then they diminish. And for the other ones, C5 to C2, they are non-crystalline and the correlations vanish at about 15 angstroms again. When you look into the zinc-zinc distances again, you see that the zinc-zinc distance peak gets broader and broader the shorter the side chain is. That means the distortion of the cluster gets more intense the further the contraction of the material is, and again, the shorter the side chain is. All right, so this is then in agreement with IR data, we see that that's a symmetric stretching vibration representative for this tetrahedron that gets very broad, and the asymmetric stretching vibration of the carboxylate gets also very broad. So that means we have different configurations. We have a distortion. Importantly, what we see in NMR spectroscopy is we do not see a free carboxylate. So the chemical shift of a free carboxylate would be about 180, 185 ppm. This is not visual, not to see. So that means we don't have a dissociation. Everything, the connectivity in the framework remains the same. We don't break a bond, we just get distortion. That is how we rationalize the data. So we did some MD calculations. Actually, Rochus Schmidt and Julian Kolb did it, because I have no idea how to do that. And they looked into a superstructure, so to model the amorphous or non-crystalline phase. So it's not amorphous, non-crystalline. Of course, you need ideally a massively large box. So what they could manage is an 8 by 8 by 8 times simulation box, so 8 cavities of the MOF-5 material. And then you see, this is a crystalline framework where you have all the cavities have basically the same volume of about 2,100 to 2,200 cubic angstroms. And in the non-crystalline phase, you have a large deviation of differently of cavities with different volumes. So you have different distortions for each of the clusters, and these distortions are also correlated. So we see here a region of cavities which have a volume of about 1,900 cubic angstroms, and here are a region of cavities which are smaller. Of course, in order to represent what is happening in the entire material, you would need a really large simulation box, which is not accessible. But this already tells us a lot about this mechanism of crystalline to non-crystalline transition in this flexible framework. All right, so we called this phenomenon frustrated flexibility because there is an interplay between the enthalpic forces in the framework, so the dispersion interactions of these side chains, and the coordination bonds. So we don't want the coordination bonds want to be straight. There don't want to be any distortion on the cluster, and these forces compete with each other. And if we only need a small contraction of the framework in order to get enough dispersion energy out, the small contraction can be done in a crystalline manner. So then we go from the cubic to the rhombohedral phase. This is the case for the material which has a C7 side chain. When the chains are smaller, we need to contract further in order to get the dispersion interactions between the smaller side chains, to get that going. And that requires the structure to get non-crystalline, because it cannot contract by a strong extent while keeping at the same time the crystalline order. And then we go into this non-crystalline states, where we have a random distortion of the clusters and interactions then of the side chains and a densification. All right, so we can do this or reverse this also with temperature, not only with gas adsorption. That is well known also for other materials already. So we can take the crystalline rhombohedral one, heat it up, and this case, the C7 one, you have a phase transition already at 325 Kelvin from the rhombohedral to the cubic phase. Same is true for the C8 one. You just need a higher temperature. You have longer side chains. You have stronger interactions. So that means you need a higher temperature to go from the rhombohedral to the cubic phase. Interestingly, similar thing also works for the non-crystalline borderline case, the C6 thing, where you have this broad diffraction features. And when you heat this material up, the Bragg peaks actually get more intense. That is very unusual. You all know when you want to solve the crystal structure of your next grade MOF, you go to a single crystal diffractometer and you cool it down to 100 K in order to get the most intense reflections. Here it's different. It's the other way around. So it's basically the Biwaller factor is telling you get a attenuation of X-ray scattering with increasing temperature, but here it seems not to be the case. So we increase the entropy in the system, but at the same time we increase the order. Doesn't make any sense, right? So what is happening here? When we increase the temperature, we do increase the entropy indeed, and the vibrations of the side chain then kick in, and the thing breathes and expands. And at the same time, the zinc atoms, the strong scatterers, go back on their lattice positions, and then we get the Bragg scattering back. So basically, we get Bragg scattering back, but at the same time, we increase the disorder in the system. It's quite an unusual case. Okay, we can follow that. So the intensity of the reflections shift, all of this, is in line with that. And we can also follow this with reciprocal space maps again. The C6 case is quite interesting because it also has a different structure when you put N-octane in it. It's cubic, yes, but it's a different space group. It's PA3 bar, and this tells us something about the structure in the dry phase. Because we look into this structure in detail, we see, even though it's cubic, there are rhombohedral distortions in this structure. But now there are two different ones. There's the acute rhombohedron, which we also see in the rhombohedral phases. And this is half of the cavities. The other half of the cavities is an obtuse rhombohedron, so one which is compressed. And these then alternate in the lattice to generate, again, a cubic structure. So there's also a method that the cubic material can contract. It stays cubic, and you have different distortions of these cavities in different directions. And that results then in a contraction of the structure. All right, final question. Is this limited to MOF-5? No, it's not. So you can also do this with other ZN4O-based MOFs. So this is IR MOF10. Yeah, we put a long side chain on there. You see the same behavior. And it also works with MOF177. You need longer side chains here, of course, because you have much larger cavities. And this brings me to the end. So the question is now, so far we were able to see this for the zinc-4 oxo-based MOFs. And I'm quite sure similar behavior can be observed for many other MOFs. You just have to look into that. And if you have any ideas, and if you observe something like this, please send me an email. I would love to hear about any other material able to do that, which has a different building unit, inorganic building unit, would be very interesting. And also, if you look into the literature, going back to the very beginnings of MOF chemistry, there have been plenty of reports of materials which are nicely crystalline when you synthesize them, and then you take the gas molecules out, and they are, people call them amorphous. I don't think they are amorphous, they are just non-crystalline. It's still the framework, and you can still do things with it, so don't throw it in the bin. Yeah? All right. And with that, I would like to thank my group, in particular Roman, who did all the work I presented today, and my collaborators in Bochum and Dortmund who contributed to this study. And I'd like to thank you for your patience and for your attention. Thank you very much.
Thank you very much, Sebastian. Do we have any questions in the room? We've got time for one or two. No questions? Everyone's a bit sleepy. Oh, there's one. Please come to the microphone, or one's coming.
Thank you. Thank you very much for your interesting talk. I want to know what will happen in the morphology of this compound after this, because you just speak about the structure. I want to know what will happen in the morphology.
Yeah, so the morphology, can I still do that? Apparently I cannot. You saw the photographs of the crystals. So the crystals are nice cubes, and when you have this transition, you get lots of cracks in them. Yeah, it still stays like a cube, but you have cracks. So the morphology basically stays the same. Of course, for the rhombohedral distortion, the morphology changes from a cubic morphology to a rhombohedral morphology. But except for the non-crystalline ones, they pretty much look the same. They just get a little bit denser.
Okay, and we have one question that's come through the stream. So Fernando Uribe Romo asks, how much does the heat of solvation and the solvent reabsorption affect the degree of crystallinity when exposing a dry sample to fresh solvent?
The resolvation is so, I couldn't get, could you repeat?
So how much does the heat of solvation and the solvent reabsorption affect the degree of crystallinity?
The heat of solvation. Okay, yes. So we chose for the octane resolvation. It works much better when the temperature is higher. We think this is due to limitations of getting the octane into the material. It's quite densely packed, distorted. The windows are narrow, and therefore a higher temperature makes it easier. For DMF, which is a smaller molecule, it works at room temperature. Okay.